Good afternoon, everyone. My name is Shaha, and I'll be chairing this session. We have 1, 2, 3, 4, 5, 6, 7 talks. This session is mostly about cyber-physical systems testing. And our first speaker presenting a journal first paper is Fabrizio.
Yes. So thank you for the introduction. Hello, everyone. I'm Fabrizio Pastore from the University of Luxembourg. Today I presented the journal first paper that was published in TSE, Data-Driven Mutation Analysis for Cyber-Physical Systems. It's a joint work with Enrico, Viganò, Cornejo, and Lionel. So this is the ICSE satellite. It's a cyber-physical system, and it runs one of the software that is used in our case study subjects, and is part of a project that we run with the European Space Agency that motivates this work. Cyber-physical systems have several components, and software is deployed in all of these components. For example, here we have the central unit, we have the attitude determination control system, we have the payload data handling unit. And when you test the software for these components, basically you have one software under test that is running on the hardware emulator. Then the other components may be simulated, or maybe you may have the hardware in the loop. The problem for companies, and especially for regulatory agencies, is to assess if the test suite is exercising the components interoperability properly, or if you want in a simple way, if the test suite is exercising the integration between the software running in these components properly. What it means is that basically you want that your test suite executes all the messages that these components are supposed to exchange. You want that all the different input partitions for the different data items are covered. For example, you want to have nominal and non-nominal values to be exchanged. And also what you want is that if an anomalous value is observed during testing, that this test case should report a failure. Now, a solution that we have in our community to perform test suite assessment is mutation analysis. It consists of injecting faults in the software under test and measuring the proportion of faults that had been detected by the test suite. The problem is that with most of the traditional mutation analysis approaches, they work by modifying the source code or the implementation of the software under test. And this is inapplicable when the software components that generate the data are fully simulated, or when they are run on expensive hardware, because you are not going to put a randomly mutated software on expensive hardware. Plus, there is another problem that if you automatically mutate the software under test, you cannot be sure that the data that it generates is not equivalent to what it was generated by the original software. So we propose data-driven mutation analysis. It consists of injecting mutation probes in the different components of the system, especially in the communication layer. These mutation probes are controlled by some fault models that are defined by the software engineers in such a way that they generate mutated data that should lead to failures. For example, basically the engineer defines a fault model that is supposed to modify the data in such a way that data belonging to an input partition is replaced with data belonging to another input partition. And then in practice, the scenario that is exercised during the execution of a test case is different than the scenario that was supposed to be executed. And so you should observe a failure in that case. So this is the idea. In practice, what we mutate is the data that is stored in data buffers, because it's a data structure that is commonly used to perform basically the serialization before sending the data. And what you have is that a data item may span over one or multiple units, and then the data represent different information, and consequently the bytes that you have in this data buffer should be interpreted in different ways, as binary, as doubles, integer, whatever. So all this information is captured in our tabular fault model, where basically we capture, we identify in each row how to mutate a data item. We indicate the position of the item, the length of the item, the representation type, and we provide the mutation operator. So the engineer specifies which mutation operator should be applied to perform a mutation and some parameters to configure this mutation operator. You can define more than one mutation operators for each data item, and we provide 12 mutation operators that we defined based on the literature and by discussing with our industry partners to identify mutations that are representative of anomalies that you may observe in the field. We have operators that replace data with data above threshold, or we have a random mutation, or we have a modification of signals. We also provide in our paper a fault modeling methodology that mainly aims to suggest the engineer how to define mutation that avoid equivalent mutants, which means that we suggest how to select mutation operators that are going to generate data that is non-equivalent from a testing perspective to the data that was already exchanged by the components. So quickly, what drives the identification of the mutation operator is the nature of the data, the dependency between the different data values, the number of input partitions, the type of input partitions, or the representation type of the data. You have the details in the paper. But for example, if you have a stateless numerical value that is used to capture the voltage that is observed in the attitude determination controlled board, for example, you may have nominal values that are between 10 and 14 volts. And so in the fault model, what you are supposed to specify is, for example, a value out of range operator that basically can be used to modify data that is in range with data that is just above the range or just below the range. Also, you specify a fixed value out of range operator that when it observes data that is outside the range, it replaces it with data that is inside the range. And it captures the idea that I was telling you before about having the modified data that belongs to a different input partition than the data that was supposed to be exchanged by these components. And of course, in such cases, you expect to observe a test failure because the data that you observe is clearly very different from the one that was supposed to be observed during the execution of the test case. From this fault model, we automatically generate a set of mutants with some technology that I'm not going to explain here in detail, but basically we end up with having different mutants. A mutant is a version of the software that contains a mutation probe that is configured to perform a specific mutation operation. For example, we have one mutant that set the voltage to be above the range, one that sets the voltage to be below the range. And so basically for each mutation operator configured for the different data items indicated in your fault model, you may end up with one or more mutants. You execute the test suite with all the mutants, like in traditional mutation analysis, and then during the execution of these mutants, we collect some metrics. We collect data to end up with some metrics. We have 3 metrics. The first one is the fault model coverage, which basically indicates the proportion of fault models having a corresponding probe that was exercised at least once. It basically, since we have one fault model for each type of data that is exchanged, it simply identifies the percentage of message types that were exercised by a test suite. And when you have a larger system, this is very useful because in the end you have a confirmation that you are exercising all the types of messages that are exchanged by the different software components. Then you have the mutation operation coverage that is reporting the proportion of probes, or if you want, the proportion of mutants that are actually mutating some data items. Remember, here we have this idea that we have one mutant that modify an input that belongs to an input partition with a value that belongs to a different input partition. So if the mutant does not modify anything, it means that it does not find any value belonging to the input partition that it is targeting. And these enable us to measure the proportion of input partition that are exercised during the execution of the test suite. And again, this information is useful because when you have a large software, it's difficult to know if you are really exercising all the inputs partition that you wanted to exercise. And this is useful as a feedback for the developers. And the last one is what we call the covered mutation score, which is basically the proportion of mutants that are modifying data and are killed by the test suite, so that lead to some test failure. And if they are not killed, it means that your test suite is not good, so actually it is providing feedback about the quality of test oracles. So this is the idea of the approach. We performed an assessment of the approach, and the subjects of our assessment are the test suite that exercise the integration of the different components of the ICSE satellite from LuxSpace and the components of the libparam software developed by GomSpace, which are two companies working in the satellite business. And basically for them we have a different number of fault models of mutation operators configured and number of mutants that we derive automatically from them. So quickly, the first research question is about the type of shortcomings that we can identify. And from our results, we have a confirmation that we identify uncovered message types, uncovered import partition, and poor oracles. And this was confirmed by our industry partners to be informative feedback that they were not aware of. The second research question is about the impact of equivalent redundant mutants. And again, we did not notice any equivalent redundant mutants. We have manually inspected all our results. And basically, we noticed that the live mutants can be killed by improving the oracles, for example, by verifying additional entries in the log files, by verifying additional state variables that were not controlled, or checking better the error messages that are already verified by the current oracles. The last question is about the feasibility of the approach. Basically, here the main point is that you have to define these fault models. And you may imagine it costs a little bit of time, but it's still feasible because we measure between 3 and 20 working hours to define a fault model. Basically, what you have to do is to read the specifications of the data that is expected to be exchanged by components, and when you read the specification, then you identify the operators to apply. And we have a little execution overhead that did not lead to any violation of real-time constraints. So it was feasible, and we were not introducing basically non-determinism in the execution of the system. To conclude, we addressed the problem of assessing the capability of the test suite to exercise properly the interoperability of the components. We proposed this idea of having data-driven mutation analysis. The empirical results demonstrate feasibility and effectiveness, and it's a journal first paper. You can find also the tool online. We have also a tutorial for the tool. Thank you.
Thanks, Fabrizio. So if there are any questions, we have some time for questions.
Thanks for your talk. A very interesting, very challenging space to assess test suite effectiveness. Could you talk a little bit about how you actually embedding into the system? Are you talking about a hardware in the loop simulation? There's a prerequisite that you can do complete software simulation? And how are you actually getting the mutations into the test suite?
Yes, so the key here is that what we do, we automatically generate an API that implements all the mutation operations that are defined from the fault model. And we automatically generate one function that we call the mutation probe. Then what the engineer has to do is to put an invocation to the function that we have automatically generated inside his call. Typically, this means that you have to introduce one function call for each message type that you want to mutate. So, for example, for those cases, I think that we had to introduce like 12 function calls to end up with 150 mutants. And this is the general approach. Then the way we performed it can be done in multiple ways. For example, in one case study, these mutation probes were introduced in the layer that was, let's say, around the simulator. In another case study, they were introduced inside the software under test. So it depends on the testing process that is in place.
Okay, we don't have time for another question right now, so I'm sure after the session you can answer more questions. So let's thank the speaker again.
Thank you very much for the introduction. So essentially what this talk is all about is increasing the diversity of a test suite for an industrial control system. But the general technique we're looking at, I hope, would also be useful for other kinds of systems that I will try to make clear in a little while. So first of all, a little bit of background. What I mean by an ICS, essentially they are just a specific type of cyber-physical system in which you have programmable logic controllers, controlling industrial processes over a network through sensing and actuating. So the kinds of systems we've been thinking about are ones that you might see in manufacturing or perhaps water treatment plants, like the one pictured here that forms our case study. So the question I care about is really this one here. Are they resilient against attacks and component failures? So for example, a sensor no longer reporting the correct value, are its defense mechanisms, its anomaly detectors, etc., able to do the appropriate thing when this happens? And so it's important to test them against the diversity of sensor and actuator manipulations to make sure that this is the case. So there are some fuzzers that generate tests of this nature using the SCADA system of these ICSs already. And I want to give a sense of what these tests can look like. So intuitively, you can think of them as a sequence of manipulated sensor readings or actuator commands that ultimately achieve some goal, so typically some unsafe state. So in this case, in this water treatment plant, the goal would be perhaps overflowing a tank, or in this example, a dangerously low pressure in one of the pipes that could cause the process to get stuck. So some simple tests that could achieve this. I have a sequence over here where a motorized valve is closed. And then in the next step, it's still closed. And then in the next step, it's still closed. Another test that achieves the same goal is doing the same thing, but for a shorter period of time. Another one would be to close the valve, but simultaneously in every other step, also turn off a pump in a different stage that is not related to this issue. And then test 56,834. Again, here we have the valve being closed. But this time we're switching the pump off and on because we can do what we like. It does not actually impact the success of this test. And so the point I'm making here is that these tests are not truly diverse in the way that I want them to be. They succeed essentially for the same reason. And in this simple example, that reason is closing motorized valve 302. So it's actually the easiest way to achieve that goal at the top. So the guided fuzzers we have for these kinds of systems at the minute, the tests they generate are basically dominated by this when it's trying to sort of fulfill this objective function. So we need a systematic way, essentially, to find tests that achieve goals like this, but for different reasons. That's the goal that we came from. But to make things more complicated for these kinds of systems, there's actually many different ways to be different. So what do you actually mean to be different in a precise sense? Are you talking about using the same manipulations across your sequence of steps? Are you talking about having a common subset? Are you talking about using the same order in the sequence? Do timing, conditions make a difference? And ultimately, there is no firm answer because it depends on the testing context. Over here, I have some white tigers, and one of them has a rainbow. Depending on what you're trying to test, maybe a tiger with a different color is fine. But maybe in another context, you want to generate a completely different animal altogether, a kangaroo. So that's kind of the analogy that I want to go with here. So the approach that we took to try and address this, we wanted to augment these existing guided fuzzers for these ICSs to become so-called causality aware. And this is basically done in three broad steps. First of all, we have some kind of formal characterization of ICS testing strategies. So intuitively, you can think of these as labeled transition systems that are expressing or constraining the types of manipulations that different testers can generate. We also formalized what it means for two tests to be the same by having equivalence classes. So we defined three in this work, looking at things like the order of the manipulations or the sets or a common subset. And ultimately, it's because there are different ways to be different. So depending on your context, you may need to choose a different class. And then finally, and perhaps most importantly, the core idea of this is as we are testing the system with respect to some strategy, once a test is found, we don't want to find tests in the next iteration that are causally equivalent to what we just found. This situation on the previous slide of 50-odd thousand tests that all do essentially the same thing. So those are the three broad steps, and because it's a short talk, I'm just going to give the gist of what's going on in each of them. So first of all, as I said, testing strategies are formalized here as labeled transition systems. So they essentially constrain the sequences of manipulations that can be generated. And there may be more different reasons why you would want to constrain this. You might want to see what can happen if you can manipulate any part of the system, or what can happen if you can only manipulate certain stages of the plant, for example. So these are just two arbitrary examples to show what they look like. On the left, this is a testing strategy that's switching on a pump and closing a valve in every single step. In the right, this is just showing that there are constraints involved, conditions rather, for different transitions. The tank level should be above a certain value in this example. And then the constraint at the bottom is expressing that actually the tester can do whatever manipulations they like, so long as one of them is opening this valve. So we express the capabilities of the testers using simple models like this. And then the next step is to essentially define formally what it means for tests to be the same or tests to be different. So for this particular work, we defined three equivalence classes that were useful for our case study, but by all means, one can define more. So we have manipulation set equivalence, which is looking at the total set of all manipulations that were used in a sequence and then comparing them. Order, looking at the order that they were used in. Or this third one, this Y set equivalence, where you examine whether a given common subset is present in all of the tests. So for this example over here, test 1 and test 3 are not equivalent if you look at the sets because of this pump 101 manipulation at the bottom, but they are equivalent under Y set equivalence if Y is set to closing this valve. So this is particularly important because this manipulation over here has been identified as causal. I'll talk about this in a moment, but essentially this is the reason why these tests are succeeding. So if we know that it's causal and we want to generate another test in the next round, we want to exclude those tests that include this manipulation so that we can have a bit of diversity. We can have a test that succeeds for a different reason to this. So with all of these ingredients put together, essentially this is what then happens. We take a goal, like overflowing a tank, reducing the pressure. We take a testing strategy, so that labeled transition system. And we take an equivalence class, which defines, in our context, what we mean is different. And then when you're fuzzing, it takes these ingredients and tries to derive tests and execute them that can only be derived from that strategy. And then once a test is successful, there's a little analysis over here, a linear time over approximation that tries to prune away manipulations that were not important for that test's success. Once that's finished, the remaining manipulations are assumed to be causal. And then it does an online update of the strategy so that in the next round, it does not derive a test that is essentially the same, using those same causal manipulations. So to give a concrete example, and this is just to give the gist, the details are explained, I hope, much better in the paper. So these are three concrete inputs. We have some test strategy over here, And intuitively, this is firing a transition once some condition gamma is false. And it's essentially saying you can use any manipulation you like except P3. It then has a successful test. So this is expressing that a sequence where you do nothing, 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 then P1, P1, followed by the set P1, P2. This apparently causes the test goal to be achieved. And then through this approximation, P1 and P2 have been identified as causal to the success of this test. And so with these ingredients, the idea of the algorithm is then to do an update of that strategy so that the next test, to get something like this, which derives exactly the same tests, except any tests that are causally equivalent to this one on the slide over here. Okay, so I don't want to go into the details of how this is working, but that is the gist of what the underlying algorithm is trying to do. So that was the formal side. We wanted to try and make this balance formal and practice in this approach. And so we implemented it for one of these fuzzers for the SWAT water treatment test bed. So we took essentially the guided fuzzing approach that takes a goal, that tries to find a way to achieve that goal as quickly as possible, but added on this formal treatment on top of it. And so what we found out by doing this is actually across the 16 goals that we targeted in this previous work, by having some causal awareness on top of this algorithm, we were able to essentially double the number of causally different tests that could be found. And I can emphasize that actually this approach can find thousands of tests, but many of them are succeeding for the same reason. So in fact, we ran it for a while and had something of the order of 50,000 or so tests, and then did a bit of pruning based on the work here, and it came down to a much smaller number. So it may still be useful, of course, to have that large quantity of tests, but if you want to force it to go into a different part of the state space, be a bit more diverse in that sense, this approach could potentially be useful. So just to conclude, essentially the problem we were addressing in this work was the fact that ICS fuzzers are often succeeding for the same reason. So we tried this idea of causal aware fuzzing to try and nudge the fuzzers into different parts of the state space and get examples that are really succeeding for different reasons than the original ones. So we saw some success when we implemented it for this test bed. But of course, we tried to be general in the way that we defined this framework. And so our hope is that it may be useful in other settings. So for example, if you have fuzzers that are based on intercepting, manipulating communication channels, there may be some use for it there, but we don't know yet. So that's just my overview of what we've done. I'm happy to take questions at this point.
Thank you very much. We have time for 1 or 2 questions.
Hi, thank you for the talk. Another way to usually to identify diversity is also looking at structural characteristics. If you don't have specifically only a code, but still you can see the flow in your system. Does it differ? Is it complementary? Did you check it?
Sorry, could you say that again? The structure flow of the system?
Yeah, structure. Test cases differ because they follow different flows.
We didn't analyze it from that angle, but typically what we observed is that in the causal naive fuzzers, all of the tests that they were generating were typically dominated by some subset of manipulations. So there are often thousands of manipulations with some important ones happening and some less important ones happening elsewhere. But beyond that, we didn't look at that.
Okay, thank you.
We have time for one more question, and maybe the next speaker can already set up his...
Thanks for the nice presentation. In the last step of your work, so basically, if I understand correctly, you do some causality analysis. Is that based on the current data set that is available so far, or is that based on...
So in this particular case, we have a successful test, and then essentially we prune one manipulation across the length of the test at a time and replay it. So where it's feasible, it can be replayed on the real system, but in this case, we had access to a simulator before then validating it on the real one.
Right. So can you say that at the same time, it's like somehow minimizing the test case into the minimal form of failure-inducing test case?
Yes, in a sense, that's what we were trying to do.
Right. Okay, thank you. Very interesting. Thank you.
Okay, so let's thank the speaker again.
So thank you for the introduction. My name is Yuqi. I'm from the University of California, Irvine. So in case you didn't know what Doppelganger means, it means a second self or a different version of oneself. And in the context of software, I think about it as multiple instances of the same software. The main subject that we're studying is autonomous driving software, ADS. They're also known as autonomous vehicle. There are many promising benefits, such as fewer crashes, increased mobility, etc. But we are not seeing many autonomous vehicles on public roads today because there are still safety concerns. So in March 2018, we see Uber's self-driving car hitting and killing a pedestrian. And in November 2021, we see Pony AI losing its driverless testing permit after an accident. So to ensure ADS safety, we have been focusing on ADS testing, and currently there are two ways of testing ADS. One is field operational, which requires a permit. And in California, only 40 companies have this kind of permit. We will see a safety driver sitting in an autonomous vehicle ready to take over in case of emergencies. And then the other kind is simulation-based testing, which does not require a permit. And this is the kind of testing that we have been focusing on. In the past few years, there have been a number of approaches published to generate scenarios to test ADS, and these are some of the prominent ones. So I'm going to briefly discuss what's common among them. So they focus on generating scenarios with a single AV and some number of obstacles. They focus on finding ADS collisions. But the question that no one answers is, do all the collisions effectively reveal ADS bugs? So let's take a look at some examples. In the first example, we have a side impact collision. The VAV and the obstacles are coming side by side. The obstacle forces a lane change. In this scenario, the AV has the right of way, and the obstacle is fully responsible for causing this collision. This scenario does not reveal an ADS bug, because there's no ADS misbehavior. In the second scenario, we have a left turn scenario. The AV and the obstacle are coming from different directions. The AV makes a left turn and hits the obstacle. The obstacle has a right of way, and in this scenario, the AV is fully responsible. This scenario reveals an ADS bug because the ADS had a misbehavior. So I think we can agree that ADS being responsible indicates its misbehavior, and this misbehavior will in turn reveal a bug in ADS. However, determining responsibility is actually very hard. When I walk up to a scene and try to figure out which driver is liable, besides the drivers themselves admitting fault, we need to look at police citations, sometimes in the insurance investigations, and in some rare cases, it may end up in the courts where the juries and the judge will be deciding which driver is liable. Now, given this idea, we can have a naive approach called experts on call. I'm going to keep generating scenarios until I find collisions, and once I do, I'm going to call each of them and look for their opinions. If they say the AV is responsible, then yes, it's a bug revealing violation. Otherwise, it's not. This approach will guarantee bug revealing, but there's too much manual work. It's probably also expensive and time-consuming. Now, maybe we can do something about the obstacles. We can improve the obstacle modeling so that they drive realistically, they respect all the traffic laws, they respect all the right-of-way rules, they react properly to other road traffic participants, so that they will never be responsible for causing violations. If the obstacles are never responsible for causing violations, then only the ADS can be responsible. But if you look at these requirements, these are also the requirements that ADS should be meeting. And we haven't seen an ADS that's perfect to this extent and never be responsible for causing violations. So we can conclude that the perfect obstacle modeling does not exist yet. So what can we do? And here is where we propose a novel testing approach called Doppelganger testing. The idea is that we're going to let the ADS control every vehicle in the simulation. And the benefit of doing that is once a collision occurs, one of the AVs must be responsible. This scenario will in turn reveal a bug in the ADS. Now, given the same scenarios that we have seen before, for prior approach, we need to ask two questions. Which car is the AV and is it responsible? The answer to the second question will determine whether the scenario is bug revealing or not. But in Doppelganger testing, we just ask which AV is responsible. And by asking this question, this inherently implies the ADS is responsible and there is a bug. Based on that idea, we implement an approach called double test. This is the first technique of its kind to go through artifact evaluation successfully, and we received badges for being available and reusable. The source code is open source on GitHub, and it's also up in the archive. You can feel free to check it out after the presentation. This figure shows an overview of the approach. We start with the map parser, which analyzes the HD map used by the autonomous driving software. It identifies the valid locations of road traffic participants, and it also analyzes for conflicts between signals at every junction. So no prior work focuses on assigning valid traffic signal at junctions. And we try to identify conflicts like the one shown on the left. If the vehicles are coming from these two directions, then signals cannot be green at the same time. And for the image shown on the right, if two cars are coming from these two directions, it's okay for signals to be green for both lanes. So after doing this analysis, this information gets passed into the scenario generator, where it will specify a scenario based on multiple AVs. It specifies where they start and what's their destination. We also specify some number of pedestrians near the crosswalk to introduce some complexity in the junctions. And finally, based on the traffic signal conflicts, we are going to specify a valid traffic signal configuration that matches the real world as much as possible. We model the green interval, we model the yellow interval, and we also model the red clearance interval. So once the scenario representation is ready, it gets passed into the Doppelganger orchestrator. This is where all the AVs get orchestrated to perform a simulation. It manages all the AV instances, initializing them, resetting them, and sending the routing requests. It communicates with each of the AV instances, retrieving their location and exchange locations before the AVs. So in other words, the message broker does the translation of the ground truth localization into ground truth perception. And by doing this, we narrow down our focus to the prediction and the planning module. So whenever a violation happens, we know the bug is in either of these modules. The orchestrator also ensures the scenario validity as long as the AVs themselves can ensure realistic movements. Now with the scenario executed, we collect the recordings and we pass them to the analyzer. The analyzer analyzes for the closest distance between road traffic participants and pairs of conflicting trajectories. These are used to promote scenarios that are more likely to involve a collision. And then we also analyze for unique decisions made by each of the AV instances and number of violations in a scenario to generate more complex scenarios. The analyzer also reports violations based on 4 oracles: the collision, the red light, the stop sign, and routing response oracle. So that's the overview of double test. Again, its source code is available on GitHub and in the archive. To evaluate Doppelganger testing, double test, we generated scenario on Borregas Avenue, which is a place near Sunnyvale, with Baidu Apollo 7.0. This is an open source version of an industrial grade autonomous driving software. We experimented for 240 hours. Oh, actually I took that picture myself. I drive 6 hours up to Borregas just to take that picture. So in the evaluation, these are 5 of the unique bug types that we have discovered, and this will eventually result in the collision. And in the paper, we talk about a case study that it eventually results in a collision because of an unsafe lane borrow decision. And I'm going to try to present this to you live, and hopefully I'll do this right. So because this is Doppelganger testing, we actually see the perspective from all 3 vehicles. We can see the execution state of each ADS. So from left to right, we have AV 1, 2, 3, colored in blue, purple, and red. If you're good at multitasking, you can try to keep up with all 3 perspectives, but I suggest you pick one, and let's see if you pick the right one that is mainly responsible for causing this violation. So at the beginning of the scenario, the blue car received a task to move forward. He sees the purple car blocking his way, so he tries to borrow the lane from the opposing direction to bypass this vehicle. And he successfully does that, and he immediately plans to return to his original lane. At this time, the purple car and the red car aren't moving yet. They are still static objects. As the blue car is returning to its line, it bypasses the purple vehicle. So I'm going to switch the ordering of the perspective to make this more clear. So from left to right, we have purple, blue, and red. the purple car is now moving forward because it received the routing request. But then the blue car, that's more interesting. He sees the incoming traffic, which is the red car, so he plans to yield to that car. And as a result, he stops on the yellow line. The red car is now moving forward. He sees the blue car is blocking his lane. So he makes the same decision that the blue car made a few moments ago. He tries to borrow the lane from the opposing direction to bypass this vehicle. As the red vehicle continues this maneuver, he sees the incoming traffic, which is the purple car. And the purple car is blocking its way. So the red car realizes, my lane borrow decision cannot be executed. So I'm going to stop here. I'm going to yield to that purple car. The blue car sees the red car is now stopped. So he continues to return to its lane. While seeing the purple car is coming from behind, the blue car decides to overtake that vehicle. So he will try to get in front of the purple vehicle. The purple vehicle is operating just as usual. He's doing his lane follow decision. He sees there's enough room on the right. And I'm not sure if you can see clearly, but the purple vehicle is not making much decisions based on the other two vehicles because they move so slowly. And that's also one of the bugs that we have identified. And in the result, the blue car continues his maneuver and collides into the purple car. And the red vehicle is just observing this bug revealing violation. So in this scenario, we demonstrate how we use 3 very high autonomy vehicles to generate a scenario. The scenario is very sophisticated, it's very complex. We see the perspective from all 3 instances of the same ADS, and yet 2 of the vehicles still end up colliding with each other. So this is how Doppelganger testing allows us to find bug revealing violations. Essentially, one instance of the software is colliding into another instance of the same software. And in prior approach, they cannot generate scenarios that are this complex because they rely on simulators' simplified obstacle modeling. These are some other type of bugs that we have identified. And in the paper, I talk about why Apollo may violate a red light based on its implementation. During the evaluation, we also submitted many issues and pull requests, and some of the bugs are confirmed by the developers. They even accepted a fix that I submitted. Again, to summarize, we propose Doppelganger testing. We do testing by observing the interaction between multiple instances of the ADS. It guarantees ADS being responsible for any violation occurring. And then we provide an implementation called double test. It's a framework that generates bug revealing violations. We discovered 8 unique bug categories in a high autonomy open source ADS. And thank you for listening. I'm open to questions now. Thank you.
Thank you for the very interesting presentation. We have time for 1 or 2 questions, please.
Hi, this is the best talk I've seen the whole conference.
Yes, thank you.
I just want to dispute slightly the idea that one of them must be at fault, because legally they often have this thing of contributory negligence.
Yes.
And in this kind of thing, you can get people, like cars would pass 1 inch apart and it would still be safe, but they've both done something dangerous. When we're doing this, we think about, is the other vehicle understanding the intention of the car, and does that vehicle meet the intention that the other person has? Like, do you see what I mean? It's like what they're doing is not preserving safety boundaries.
Yeah.
Like, how would you explore that kind of safety boundary thing with this kind of technique?
Right. So if I understand your question correctly, so sometimes the car violates some laws slightly to complete its maneuver. Is that what you're asking?
It's not technically a violation of the law.
Yeah.
Until it crashes in some cases.
Yes.
But the safety margin is being reduced.
Yes. So that's why in our testing, we only implement the collision oracle. We only detect collision in the end. And once the collision is detected, we look back into the scenario and we analyze for what was the suboptimal decision that caused the violation. And that's the bug types that we have listed later. Yeah.
Maybe the next speaker can already...
Thanks a lot for the great talk. I really enjoyed it. It's a super nice piece of work.
Thank you.
I'd like, though, to question in a constructive way, because I really like the idea that responsibility implies a bug.
Yes.
Going back to the first example you had in which one car is driving into the other one, the non-autonomous car is driving into the other one. Yes. I would still expect the autonomous car to be able to brake in time and avoid it. So that would be, then the car is not responsible, but if it's not, in some conditions, if it's not able to brake and stop in time, I would still call that a bug, a faulty behavior at least.
Yeah.
So
I think the question comes to whether the purpose of autonomous driving software is to drive us to the destination safely, or is the purpose to avoid all kinds of collisions. So if the obstacle tries to cut into you on purpose, in real world, we cannot do much as real human drivers. So the developers of the ADS cannot do much, do not have much control over what the obstacles does. That's why think about Doppelganger testing. We just look at when the ADS is making suboptimal decisions, rather than when it's not reacting to bad behaviors like we've seen in scenario 1.
Let's thank the speaker again.
Great, thank you so much. As you said, my name is Trey Woodliff, and I'm going to be talking about our paper, Generating Realistic and Diverse Tests for LiDAR-Based Perception Systems, done with my colleagues at the University of Virginia. So first, to understand this, we need to have a common language of knowing what perception is in this context. Generally speaking, perception is turning sensor readings into actionable knowledge so that we can navigate around our world in a safe way. But specifically for our talk today, we're going to focus on a type of perception called semantic segmentation, where we label each element of the sensor data with its semantic meaning. So here, in the context of pictures, because those are easy to understand, we have labeled each pixel with what that pixel represents. The road is purple, the people are red, the cars are blue, and so on. But modern autonomous vehicles have more than just cameras on them, and so to get a feel for that, here is a video of a Waymo vehicle driving down the road. We're familiar with cameras, but then it showcases its LiDAR sensor that's sending out beams of light that are reflecting back to give this 3D point cloud that shows it how far away it is from all of these obstacles. But this looks very different than how you and I perceive the world, so I took that point cloud, and now we're looking at the bird's eye view in perspective. And instead of color, we have the reflectivity of the surface that it bounced off of. So this is what you should keep in mind. This is what we're doing today, but this is very hard for us to think about. So I'm going to then project it back down. So now we are looking through the windshield of the car out, projected onto this 2D plane. But this is a very 3D problem, just hard for me to show you that. So just to get a feel for how difficult this is for us to reason about, I want some audience participation. How many cars can the LiDAR see right now? We're doing perception. We need to know how many things there are in our environment. We need to be able to move safely and reason about them. And this is a fairly difficult problem. I'll be very surprised if anybody found all of them. There are actually 11 that I have colored for you now in blue. But the problem that we're trying to solve is even more complicated than that. I don't just want to find the cars, I actually want to find everything in the whole scene. So if I were to ask you each individual point, what does this mean? How could we solve that problem? And this is very important, as the previous speaker alluded to, these are safety critical systems. In 2018, an Uber autonomous vehicle driving along the road at night, it was dark, the camera wouldn't work. So it was relying on the LiDAR perception system to perceive its surroundings. And tragically, it was unable to see Elaine Hertzberg crossing in front of the road. It hit her, and she was fatally killed. 2 notes from this. The system could not determine whether Hertzberg was a pedestrian, vehicle, or bicycle, and therefore could not predict her path. Only 1.2 seconds before the fatal crash was the system able to identify her as a bicycle moving into the path of the Uber, but by then it was too late to take evasive action. So this just highlights the criticality of making sure that we can perceive our environment accurately so that the downstream task can perform safely in our environment. So what do we want to do? We want to generate LiDAR perception tests that are diverse to capture these safety critical edge cases. Not many of our test cases have the person walking in front of the vehicle, but we need to do it in a realistic way so that we can make sure that these tests generalize to the real world. And what do these tests look like? Well, we've been seeing them along the way. We have this test input, which is the LiDAR point cloud, again here visualized in 2D, and the expected output, which is the semantic segmentation labeling every point in the image. And so how do we do this right now? Well, generally we have this trade-off between realism. I can go run my system outside and see what sort of data I can encounter. But ethically, we can't capture the data of people walking in front of the road. And so we're very limited in the diversity that we have there. Okay, well, we can simulate that, but then we trade off the realism, and we're limited in knowing how well this is going to generalize when we do encounter this in the real world. And so that's where we introduced the idea of semantic mutation testing, which was an ICSE 22 paper. And the key insight here is that we have domain-specific mutations of images that preserve realism by construction while expanding our diversity. So we can use real data to generate realistic and diverse test cases. But there were several limitations here when we tried to expand to the other sensors that are used by modern autonomous vehicle systems. We had this implicit reliance on the 2D image domain. We couldn't find the type of safety critical failures that happen in these other sensors, and there was only manual false positive detection. I'm going to cover some of the ways that we solved these weaknesses for LiDAR. I encourage you to read the paper for the other solutions we had. So now we're going to talk about our approach. It's divided into 3 stages. We're going to go into each of these in detail, starting with the resource collection phase, where you take the real data so that we can then enrich our test cases. So we start out with this LiDAR point cloud, and we assume, for the purposes of our work, somebody has already provided us with a ground truth semantic segmentation. There are a handful of these data sets that exist. They were very expensive to collect, but we have them, so let's use them. Once we have these prior annotations, we go through and we perform entity identification to pick out the key elements of these that we can then use to enrich our future test cases. So let's say I want to work with cars. I will go through and pick out all of the cars that we found earlier. And just to show you what it looks like, the individual car looks like this collection of points. But then we want to filter out these cars, only those that are going to be suitable to add into our test cases later that we can provide sufficient definition to in order to do our mutations later on. And so what we get at the end is this set of input-output pairs and a collection of entities in these environments that we can use to build our test cases. Once we've done that, we want to generate our mutations to improve diversity. And how do we do that? Well, each mutation consists of a set of composable basic transformations. So here we take our input-output pair and the car that we found from before, and we're going to embed this car into the mutated test case. And I'll give you a better image that we can see later on in just a couple of slides. But crucially, each of these basic transformations has a real-world motivation. I want to do these in order to diversify, but in a way that I could plausibly see in the real world. These safety-critical edge cases that we know could happen, but we likely don't already have in our data set. And crucially, we need to respect realism invariance to make sure that I gave you real data, and you preserve that realism throughout the operation so that when we get out, we have data that sufficiently reflects the real world. In our paper, we explored 8 of these transformation operations. I encourage you to read the paper for the full implementation details. We're going to focus on this add operation for now. It's one of the easiest to understand visually. As we said, we want to be able to capture these operations that we know are going to occur in the real world. So in order to capture a person walking in front of the vehicle, well, I'll add a person walking in front of the vehicle. And so we have this real world motivation, but then we also need to respect invariance. The person can't be floating. They need to be in the place we want them to be. And so in doing that, we can build this mutation to give us the data that we want. So the original image, we have the LiDAR on the right and the expected output on the left. We take the car that we found before, and now I can insert it into the specific location just off the roadway, somewhere that we might try and hit it, or try not to hit it. And so now, once we have all these mutations that we've been able to diversify our test suite, we need to evaluate the systems under test on these, which is how we evaluate our system. For brevity, I'm going to merge this into our evaluation section. I encourage you to read the paper for separate details. We evaluated 3 different research questions, but just for now, I'm going to focus on our ability to find failures in these state-of-the-art systems. We looked at 5 state-of-the-art systems posted on the Semantic Kitty benchmark. It's important to note these are from both academia and industrial partners, and so these are truly state-of-the-art systems trying to solve this task. In order to assess performance, we need to figure out how to find meaningful failures. In order to do this, we're going to pick out continuous metrics, such as accuracy, and then we're going to threshold how much accuracy drop we can have in order to show a level of failure. And this can be tuned for the types of failures that you're looking for. And so what does this look like? Well, one of the test cases that we found, I know there's a lot going on here. Over on the left, over on the right, we have this car. It was mutated ever so slightly, and it caused this huge change on the left-hand side. So the orange is fence, the yellow is building. And we can see that changing this car on the right caused the fence to turn into building. You may say, okay, well, fence, building, what's the difference? Those sound similar to me. But this just points to the general brittleness of these systems, that a small change in one area can lead to a large change somewhere else in the system, and this could point to some underlying failure that we should investigate. This is a 21% drop in accuracy. It's very easy to find these things. But we're not always so lucky. Sometimes there are very small parts of the data that can lead to very critical failures. So here we're looking all the way down the roadway. There's a cyclist going along the side of the road. And so I've highlighted in white here the cyclist entity down the roadway. This was the expected output. When we actually ran this test, the system identified it as this blue and red region over here. And the blue is bicycle and the person is red. And you say, okay, well, a cyclist is just a person in a bicycle. That sounds fine enough. But actually, under the labeling scheme that we have, a cyclist is mobile, as in I'm riding the bike, but a bike is a stationary entity. So a person standing next to a bike, behaves very differently from a cyclist. And if I'm going to hand this to my downstream navigation task, it needs to know the difference between the two. Otherwise, I may not be able to safely identify them and take the action I need. But the problem is, this potentially safety critical failure only affects 0.03% of the points in the point cloud. So we're not going to be able to find this using our accuracy drop means, which leads us to the Jacquard metric. Here we classify success based on its performance across the different classes. There are 19 different classes that we have. Even if we have 95% success in all of the other classes, except for pedestrian and bike, this will still reveal a failure because we'll only have 89% accuracy on the Jacquard metric. So now going back to the previous example, this 0.03% drop in accuracy actually leads to a 7.5% drop in the Jacquard metric because this one class was so catastrophically mispredicted. And this allows us to pick out these types of failures in these systems very well. So can we actually find these failures? We evaluated on just under 67,000 tests across 7 different mutations. And we were able to find up to 100 mutations across the different systems that we tested using the accuracy metric. I'm going to adjust the scale here as I add in the Jacquard metric, and we can see that these very small failures are actually much more common than these large accuracy failures, as we may expect. And just one thing I want to point out here, as we move left to right on this slide, these are in order of their performance on the benchmark. So Cylinder 3D was actually the #1 performing perception system on the benchmark, but it has the most failures under the Jacquard metric. And so this may point to the limitations of the benchmark data sets. These are also the same data sets that we're training on. Maybe we need to find more data to move this problem along. So it's some interesting future work. So to conclude, our technique can leverage real-world data to generate diverse tests while preserving realism to find failures in state-of-the-art perception systems. I encourage you to scan the QR code, go to our GitHub repository. There's a lot more information there. I'm happy to take any questions.
Thank you for the very interesting talk. We have time for questions.
Hi, thanks a lot for the nice talk. I have a question concerning the mutation that you do, and also related actually to the example about the bicycle and the cyclist. So all those discussions seem to be about the mutation of a single frame. Are you also mutating streams of frames? Because that would help perhaps the machine to distinguish the moving entity from the steady one.
Yes, it's definitely well taken. All of the work that we have done, and I presented to you right now, is on single snapshots. The performance may not generalize to streams. These systems behave very differently when they are done in sequence. We have been working on trying to adapt this to continuous time. It's a much more difficult problem. If you have any insight on how we might make sure that we're generating tests that are realistic across time, I'm happy to talk about that. But point well taken.
Let's see. Thank you. It's a really hard problem.
Any more questions? We have time for a question.
All right, well, thank you much for the presentation. The question I will have also about the mutation, right? So if I got it right, you apply one-time mutation, right? It's just first order. So what happens if you ask higher order mutations? So, you combine multiple things. Could be one single feature in isolation does not lead to the failure, but if you have a bicycle on the left, a bicycle on the right, and other things. So is there any idea on follow-up for higher order mutation for this type of work?
Yes, that's a good point. As presented, I was a little bit imprecise in how I described it. The individual transformation operations that we have are already somewhat combined. So, for example, we have the add mutation, but sometimes I will edit the entity before I add it, but then I don't try adding 2 different entities to the same scene. So we did a sort of first order composition of them, but yes, doing multiple compositions. The idea of the realism invariance is that once I've generated a new test, I could just put it back in my test set and keep doing further mutations on it because it should just behave like any of my original test cases.
All right, thank you.
Right, thank you.
Okay, let's thank the speaker again.
I'm Elson. Okay, so today I'm present the joint work with my colleagues in the University of Milan Bicocca, and Dario is from RFI company. and my colleague Yuntianyi is in the audience. So today I'm talking about automated test case generation for the SCADE programs. So we targeted in safety critical softwares for our industrial partner in railway domain. So as a team, we are developing ETCS, developing and testing ETCS, stands for European Train Control Systems. So which is a critical system that handles the signals, control, and the control onboard equipments in train for the train protections. So for example, like if the train passes the permitted speed to slow down the train, the ETCS receive the signals from the trackside subsystems, and the onboard equipment needs to stop the train. So the specific important fact is that the ETCS is developed with the domain-specific language called SCADE. So which is largely adopted in many industries like Airbus, ISRO, Rolls-Royce, and many more. So the developments are based on the state machines. Here we can see the state machines. So let's consider the state machines as a working model in the SCADE program. So of course you don't want to understand the entire details of the state machine, but let me give some ideas. So this program, the SCADE program for regulating the train protection when it grows some critical points. So here you can see the different states and the transition to handle these situations. If the train needs to pass a non-protected level crossing area, the onboard equipment shall update the end of authority, which means temporarily start supervising the train and release the train when it's crossed the end locations. So that's a basic idea of this state machine. SCADE automatically translate this state machine into a equivalency code with the help of KCG compiler, which is a core compilation toolchain of SCADE suite. And this generated codes guarantees the EN 50128 functional safety standard for railway domain. So what I'm talking today is we need to automatically generate the test suite for SCADE programs, which was motivated from our industrial project, which aims to reduce the testing cost and need to achieve a structural coverage, high structural coverage. And it is important to do that, in the systematic testing approach to meet the certain certification requirements. So we investigated the well-known state-of-the-art technologies, symbolic execution with CLE, bounded model checking with CPMC, and search-based testing with AFL. So but in the same time, like as a researcher, we know that we are aware about the state-of-the-art technology have a lot of open challenges, like like path expulsion, pointer aliases, dynamic memory allocation, limitations of constraint solvers. Yeah, but this intuition had, but the intuition we had in the beginning is like the restriction of this code that automatically generated from the SCADE program can mitigate them. Okay, so in particularly the restriction that confirm our intuitions are the generated code does not contain the pointer arithmetics, pointer alias, no dynamic memory allocations, no recursive data structure, no recursions, no loops with unbounded conditions. So by considering this, we investigate our approach by developing a tool chain called TEX, which stands for Test Engine for Critical Softwares in SCADE. Out of this C program generated from the SCADE, the TEX connect with the tools, CLE, AFL, and CBMC that allows to automatically generate the test input. So as a result, from the result, we are able to convert that test input to the test script for the SCADE. So in TEX, we have two important phases. The first phase is the test driver, and the second one is the test synthesizer. Let me give example. So the first index, the converted C program, we need to add with the test driver. So the main reason is throughout the experiment phases, we need to unfold all the fields of, unfold all the inputs and then assign the fresh values, then execute the target program many times. Then run one of our tools to automatically generate the test inputs. So then translate the test input into the skate format. In detail, the test driver analyzes the executions in multiple cycles. So for the skate programs, that to find out all the input for each execution cycles. So, sorry. This will unfold all the fields of data structure in any nexting level, since the fields are necessary to be finite. So, and also we need to call the target function to reach in every state. So, which gives an exercise that all we reach the all paths and execution sequence at least once time. After compiling the C program, the test can generate the test data for each fields of execution cycle. So here the figure shows the text input from the text that correspond from the text, and it can fetch the informations, enumeration values which are belongs to enum data types. So here I just show in the tabular format just for the presentation purpose and understanding. The test synthesizer will translate the test inputs into the skate format. So here the figure shows the test cases generated by our tool for our working model. Okay. So you need to just note down the two keywords like SSM set, which provide the input for the models, and SSM cycle that used to move to the next phase of the next text steps. So the highlighted ones are the underlined ones are the values which we show in the which we seen in the previous slide. The tabular format we need to convert into the skate format. So we selected 37 skate programs which are belongs to onboard signaling unit for the high-speed railway systems developed at RFI. So I'll give you a few examples, like for example, cross-non LX, which are the we already saw as a working model, which is a procedure that monitor the level crossing area that's not protected by any external authorities. And for example, Bally's info, so that gives the driver gets the messages from the railway trackside transporters, and emergency one, which updates the onboard data once the emergency message is received. So yeah, these are the figures of state machines under some functional sub-functional implementation of level crossing procedure. So like this, the most of the models are like this, and it seems to be complex in the implementation. So let me show you some interesting results. So as per the requirement standards, we measure the observable modified condition decision coverage for 37 subject programs. So we calculate the model coverage using the test case generated by each versions of our text version. So with the text CLI, text CBMC, and text AFL. So from this plot, it is clear that CBMC and CLI is able to achieve the high structural coverage with a median of 91%. So, and also like as we know that the search-based testing is hard to hit a good structural coverage. Then it's an interesting point is that like the tools are complementary. So when we merge the test cases, either like the CLI and CBMC, we achieve the high model coverage for 15 subject program out of 37. Then we try to continue the same thing with the other combinations with the CLI and AFL, we got 14, and the CBMC and AFL, we got 13 subject programs. So this is the summary or overall the coverage we can merge with all the test cases from our text version. So from this, we can achieve the high model coverage with a median of 94%, which is good for the system. And we got the coverage more than 90% in 31 subject programs, and almost we got more than 80%. So the another data shows the efficiency of our test cases. So the number of generated test cases should be, it should be in the manageable size. So here we have within the range between like 1 to 56 test cases. So it is important to that because our the software testers have to adopt the manual assertions to the test cases. So with these manageable test cases, it is possible. And with those test cases, we revealed 7 previously unknown faults in 4 subject programs. So for example, one is 1 out of 4. It's like a missing update of state variables. So, and this, like these faults, we are finding these faults. We feel like that these reports support the usefulness of our test suite generated with our tool text for the component level testing. And this data shows, this table shows that the test is able to achieve the execution time in manageable budget time. So we put the time budget as 5 hours. So for example, with the CLE, only for the shunting procedure, it goes out of the 5 hours for the symbolic analysis. And for the CBMC, we put a unwinding loop with 1,000 values to complete the execution in budget time. And for the AFL, we consider a uniform execution time for 5 hours. So it's a mutation analysis. So we consider as a 5 hours or as a budget time. So yeah, with this, I'm summarizing my talk. We introduced the test generator for the skate programs, and we are able to achieve the high model coverage with the manageable test cases. Yeah, and we are continuing our research for supporting the integration testing. Thank you all.
Any questions?
Thank you for the nice presentation. So my question is, so you discovered 7 unknown bugs. I just wondering, where does this kind of bugs come from? Is it coming from the code generation part, or do you have any suggestion to fix such kind of bugs in the future? You know, if we use the same KCG to this same kind of bugs may come again later. Yeah. Thank you.
Yeah. So as I said before, like we find out the bugs when we write the assertions manually, so which matches to the requirement document. So as the person who was doing the testing analysis, he is able to find out the bugs easily, and he can fix it in the implementation parts. Yeah. Thank you.
Okay, so let's thank the speaker again.
Hi everyone, my name is Christian. I present you how we prioritize test cases for self-driving cars in virtual environments. As you know, self-driving cars got more and more popular, but unfortunately there were already deadly accidents. So this requires more proper testing of those systems. We can go either into the field, real world, and test those systems, but we then have the problem of not having reproducible tests. On the other hand, we can go into simulation environments and test more deterministically. For this, we need a simulator. We use BeamNG as a simulator, which comes with a practical Python API. You can program the scenario and also assess the sensor data. So when we talk about the Oracle in our context, we focus on the lane keeping ability of the car. So when the car is able to follow the lane, then the test passes. When not, then it fails. So when we talk about test prioritization, this is in the context of regression testing, which consists also of test selection and test minimization. So we assume we have already selected test cases, but now how do we prioritize them? So when we take a closer look at the simulation-based tests, they have a common issue. They are quite expensive in terms of execution time. In our case, with BeamNG, a single test case in average takes 49 seconds. So we come up with the intuition that we should minimize the test execution cost early in the testing process and also provide maximum diversity early in the testing process. So we do black box testing, and we need for the measure for diversity input vectors where we can apply distance metrics on it. We use the Euclidean distance metric. So, but how are such input vectors built? So we use road features for that. So road features are, for example, the length of the road, the direct distance from the start to the end point, but also the number of left and right turns, but also the angles of the turns. There are also a couple more road features you can look up in the paper. So we have simulation-based test descriptions. We extract the road features out of them, and then we construct the input vectors where we can calculate the distance metrics. As you see, a test suite is a sequence, a permutation of test cases which consists of road features. We want to minimize the testing execution costs early in the testing process and diversify test cases in the beginning of the testing process. So this is an optimization problem we solve with a genetic algorithm. So we apply single and a multi-objective approach. For the multi-objective, we use the NSGA2 algorithm with the knee point selection. The knee point is the closest point to the utopia point, which comes with the best parts of both extreme of the Pareto front. So we have an initial solution, which is a test permutation. Then we select the tests based on the objectives. We do the crossovers by creating new offsprings, and then we create further offsprings by mutating them. We evaluated our approaches with two baselines, a random prioritization approach and also with a greedy algorithm. We take a closer look at this graph. This means for the same time unit, the random prioritizer detects 87 faults. In the same time unit, the single objective approach detects 176 faults. The greedy algorithm a bit more than 200, and the multi-objective approach 234 faults. And this is just for one AI setting, which reflects a safe driving style. But this result is consistent among different AI settings. So overall, our multi-objective approach outperforms all other approaches. To wrap up, we do simulation-based tests on system level. We need to prioritize them, but in a way that we minimize the execution cost and maximize the diversity of the test early in the testing process. For that, we use a genetic algorithm, and the multi-objective approach outperforms all other approaches. Thank you very much, and I'm open for questions.
So we have time for one question. Please, here.
Thank you very much. So you were talking about using the Euclidean distance of the vector space to talk about the diversity. If I understood that correctly?
Yes.
Does that favor certain elements of the vector space? It looked like you had two different features that were like 2 orders of magnitude larger in range than the other ones. Can you speak to that?
Yeah, I did not get into details. We normalize the values of the vectors, and then of course some values are not on the same scale as others.
So would you want to favor certain elements of the feature space? I went from asking that, why are you favoring two?
We did also PCA analysis in the paper, and for example, the road features I presented more clearly actually contribute more to the diversity and also for the fault detection.
Thank you.
Yeah.
Okay, let's thank the speaker again. And
So yeah, I'm going to be presenting our work that was done in collaboration between Ireland and Japan with NII, and I was in UCD at the time. You can actually have a little game of comparing between the journal version and the first slides, where everyone is. We moved quite a bit. So what we looked at in this paper was trying to get some coverage for ADS testing. We've heard a couple times during this session that one thing you can do to test your autonomous driving systems is to use simulations and scenario-based simulations. So you have a bunch of different scenarios, taking roundabout, going around a corner, and that. You have a simulator in which your autonomous driving system is simulated, and then hopefully you have test results that tell you that you didn't crash, everything is good, and your autonomous driving system is safe. If not, you go back and change your autonomous driving system. Question when you do that, though, is are our tests any good, and do we need to test more? So to try to answer these questions, we came up with what we call parameter coverage. And the idea is, so we have our tests, we have our simulated ADS that gives us test results, but our ADS has a bunch of parameters that decide how it takes its decisions. So for example, the safety distance it takes, how fast it's happy to go, how much it cares about safety regulations and all that. So what we do is we play with the values of those parameters and we replay the tests. And if our tests are really challenging our system or are really exploring the space of its decisions, changing those parameters should lead to different results. Maybe, maybe not. So we rerun those mutated versions of the ADS and we check, did we get different results? And that gives us basically a coverage matrix saying, this test led to, detected this change in parameter, but not that one, not that one. So, for example, here in my matrix, test one is pretty rubbish because I can change my system however I want, I still pass the test. On the other hand, test 2 seems to be doing quite okay. So that was the idea we had, and we did that with a pretty simple simulator. It worked well, we had nice results, great paper, we're very happy. Turns out when you go into more complex systems and simulators, you get an uncertainty. You can run the same system, simulate the same system in the same scenario multiple times. It won't take the same path. So you'll have different results. Question is, are my different results because of the uncertainty in my simulation or because of my mutation? So now we can't really rely on just comparing the results of the original mutated system anymore, not in a raw manner anyway. So how did we overcome that challenge to move to those more complex simulators? We still have the original ADS. We still mutate our ADS. But this time, instead of running things once, each system once and comparing, we run them multiple times and we call to the magic of statistics. You can always get statistics somewhere. They'll always solve all your problems, most of the time. So how do we do that statistical comparison? Well, it depends what we're comparing. One of the things we look at to see if the original system and the mutated system are different is we look at just the basic path it took, so the positions in time. What we do when we compare that is we take the different paths for the different simulations of each system, we get mean path, so we just average everything, and we check are our two mean paths more distant than the standard deviation, basically. So we check, are they more distant than the noise at any point in time? And if they are, we conclude that the results of the mutated system are different. Our test covered our mutation, we're quite happy. Sometimes we also look at things like safety and comfort, which give us numerical values. For example, for safety, we look at the minimum distance with all other objects in the simulation throughout the simulation. So when we do that, when we run our multiple simulations, we get a distribution for the original system, a distribution for the mutated system. We apply a Mann-Whitney U test between the two distributions to see if they are different, and then we get an A12 to see if, for the magnitude, and if the magnitude is big enough, we say that the test detected the mutant. So that's how we did that. So how we got to do coverage for those ADSs, so to get an idea of how good the tests are in this context of uncertainty and uncertain simulations. So we compute our parameter using mutation, because we can't try every value of every parameter, so we try some changes of the parameter values. And don't really have time to talk about all the results, but there are very nice tables in the paper if anyone wants to read that on their plane home or whatever. So we implemented it, we applied it to the autonomous system, and we found that the coverage is achievable, so we're not setting impossible test targets, and it distinguishes between tests. And we also find that it had a nice thing of being monotonic, so if you detect a small change, most of the time you detect a big change, and that means we can play some nice tricks to make it faster to execute. So that's it. Thank you very much.
Thank you very much. We have time for one question. No question. I have a question. In the last slide here, you say it's expensive, but we can be smart about it. Can you say 1 minute about this?
So, I mean,
why it's expensive?
It's expensive mutation analysis. You create mutants of your system, you have to run your tests against your mutants. Tests take a long time to run. I mean, mutation, expensive, you can't really get around that. But as I said, it's mostly monotonic. So if I have if I detect a small mutant, most of the time I detect the big mutant. So I can prioritize the way I look at my mutants to make things faster. So if I detect the small mutant, I don't have to bother to run my test against the big mutant, because I've already detected the small one. So you can do those kinds of tricks to reduce the number of test runs you have to do to get your coverage. Thank you very much.
So, by this, we thank the speaker again, and this session is over, and everybody is welcome to the closing session of ICSE.